Here we go. Okay. Welcome to the first of many talks by the Mathematical and Computational Sciences Society. Today we have our esteemed guest, Ilir Dima, and he's gonna tell us about the shape of data.
Thank you very much. Thank you for the invitation. I mean, I'm really happy to do this, like, to be honest. I mean, so like, I hope you'll find the talk interesting, but at any point, you know, like, feel free to interrupt and ask questions, you know, like, as you guys see fit. Right, so the shape of data, drum rolls. So like, why do we need it? Well, if I can only figure out how to switch the slides in here, which, okay, good. Okay, so the motivation is really to analyze data with rich geometric structure, right? So that's the end goal. Right, so how to get started and what is the motivation? Well, humans are, you know, like, provided with an innate ability to detect shapes, right? So this innate ability, like, neuroscientists believe that it is gained around 4 to 5 months, like, old, right? So basically, since we are babies. Nonetheless, you know, like, for a very long time, you know, the shapes that we can reliably recognize, and I mean, we can recognize tons of things, but the shapes that we can reliably name, like in day-to-day life, they are quite limited, right? So circle or a ball or maybe a straight line or a rectangle, a triangle, and so on, right? So how do we actually reliably describe more complicated shapes, right? Like, further, is there an automated way? So basically the end goal is, right, to help us automatically recognize the shapes, right? So like, is there a good way to describe, you know, like, the shapes in a formal way so they can be recognized by your computer? And furthermore, like, is there shapes, like, in data sets that are not very geometrical? Like, what I'm talking about, like, for example, we're going to see, like, an application towards the end of the talk in the connectivity structure of different brain regions, right? So that connectivity is not measured by geometrical proximity of clusters of neurons, but it is rather measured by the correlation, like, in terms of the functional connectivity between clusters of neurons. So like, how can we actually, like, say reliably that, say, like, in a normal brain, so to speak, under, like, a certain, you know, with certain value of correlation, we have that many connected components, and if this correlation changes, how many connected components we do have, or if we keep the correlation fixed and we change, kind of like the kind of brain. So if we looked at the normal brain, for example, and at an Alzheimer's patient's brain, you know, like, can we distinguish, you know? So basically, can we use TDA, topological data analysis, as a diagnostic tool in medicine, for instance, and many other applications as well. So like, for starters, please, somebody speak up and tell us, like, who are these lovely Pokemon that you see? Come on. So there is something on the chat. Okay, so like, yeah, one of them, yeah, the middle one is indeed the yeah. Okay, okay, so the left one, yes, this is the right one. And the left one is actually Ghastly, right? Yes, okay, so great, okay, great. So yeah, like, we got the answers. Very well. On the other hand, we do see that Ghastly as a Pokemon is basically like a giant blob, right? It doesn't have many features, right? It has 3-side individual or 4-side individual small components, but the majority of it is concentrated in a giant ball, so to speak, or in a shape homeomorphic to a ball, right? And the two other guys, they basically have holes, right? So like, one of them has 2 holes. The other guy, what is called the Grengar, like, has 3 holes, and the hunter, the middle Pokemon, has 3 connected components and 2 holes, right? So basically, there are 3 connected components in it, right? So by giving this description, right, we just like describing some features, right? So is there a good way to recognize these features automatically? And further down the road, like we know that we are pretty good at determining shapes by connecting the dots, right? So same question prevails, like you can identify these Pokemon on your own, like feel free to put them on the chat if you like for fun. But I mean, the point is how can we actually tell who these guys are automatically, right? Yeah, so let's start with points, right? So basically the simplest geometrical feature that we can distinguish anywhere is the point. Point is also zero dimensional, right? Now, like as we move in dimension one, the simplest one-dimensional shape is basically one segment, right? You can take this as a unit segment, but really the magnitude of it doesn't really play a role. If we move on into dimension two, the simplest shape that we can talk about is the triangle or the two simplex, right? And as we like ramp up the dimension, like we distinguish the tetrahedron or the three simplex. You can continue doing that in higher dimensions, but the geometrical intuition often is harder, like to be explained in higher dimensions. So why are these guys helpful and where is the connection? Well, the end goal is how to actually distill like a formal way, right, to say reliably that this shape is a circle or something homeomorphic to a circle or a ball or something homeomorphic to a ball, right? Or a donut or something homeomorphic to a donut, for example, a teacup, right? How do we do that? All right, so it turns out that simplices do help us do that, right? By offering us a nice way to triangulate virtually any manifold. Right? So under certain mild conditions, one can prove that any manifold can be triangulated, which means it can be covered by simplices. Right? So it's not very hard to see this in dimension zero, it is trivial, right? In dimension one, I mean, you can take any curved, like any curved line, and you can split it into a random number using a random number of points. And if you connect these points with segments, you can homeomorphically map these segments to pieces of the curve, right? So that's a triangulation in dimension one. A triangulation in dimension two, like would be something similar, but you use triangles to do it, right? So for example, you take a ball, you can, define curvilinear triangles, or you can start with rectilinear triangles, which can be mapped into curvilinear triangles. Now, if we look at the process a little bit more formally, right? So just look at the triangle that we have in the image, right? The starting point is the three vertices. In an abstract sense, we can take these three vertices as abstract vectors, right? And we can form linear combinations of those. For example, the C naught is a linear combination of two simplices of dimension zero. Right? This is formally called a zero chain. Are there other zero chains? Sure. 2a plus b minus 3c, 9a minus 12b plus 42c, etc. Right? We can do the same thing in dimension one, but simplices in dimension one are the line segments, the sides of the triangle, labeled by lowercase letters. Likewise, in dimension one, we can take all these three simplices and we can linearly combine them using coefficients. Where do coefficients come from? We are interested to form vector spaces. Why vector spaces? Because we can construct maps between vector spaces. Why maps between vector spaces are interesting? Because it's the tool that it is best understood in mathematics. If you can turn something into linear algebra, then you can do anything you want with it, right? You can basically apply Gauss and whatnot, like all these like beautiful algorithms that gives us like a very good understanding of the structure of vector spaces, the maps over vector spaces, their subspaces, and so on. So what would be interesting, like, and how it would be interesting to map between these two vector spaces. So right here, we can form these two vector spaces. We can take uppercase A, uppercase B, uppercase C, and form these linear combinations of vectors, uppercase A, uppercase B, and uppercase C, right? Since these 3 points are linearly independent, right? The vector space that we get is 3-dimensional. Likewise, if we move to simplices of dimension 1, we can do the same thing with lowercase a, lowercase b, and lowercase c. We get another 3-dimensional space. What is interesting to notice is that the boundaries of these segments, for example, segment lowercase a, are the uppercase a and uppercase b. And if we choose an orientation, right, the expression of this orientation would be a special chain, which would be b minus a. Basically, if we orient the segment basically from a to b, right, we can have this b minus a that indicates this fact, right? This chain b minus a that indicates this fact. But now, this way we can construct a map, right? So like we can take the difference of the vectors b minus a minus c, b minus c, whatever the orientation is, right? You choose an orientation and form these combinations, and we can form a map by mapping these 3 differences to the basis of the other space, right? So we know that in order to create, to generate a linear map, right, we just like need to have a way to map basically vectors of the basis to the vectors of the other basis. And this map does give us this possibility, and we extend it by linearity. Okay. So basically we map lowercase a to the difference, say like b minus a, right? Lowercase b to c minus a, and lowercase c to b minus c, or c minus b. Like now I can't tell the orientation because I failed to put the arrows of the orientation, but you put the arrows of the orientation and you build this map reliably. Since we can map these 3 lowercase vectors to a linear combination of vectors of the basis of the space of capital A, capital B, capital C, right? We can also talk about the image and the kernel of this map. These are obviously, like, one is a subspace, the image is a subspace of the vector space generated by capital A, capital B, capital C, and the kernel certainly is a subspace of this of the vector space generated by A, B, and C. It turns out that the dimension of the kernel is 2, right? So like turns out the ratio, like if we like to form the quotient space, like of the image over kernel, right? This vector space, the quotient space, has dimension 1. And it turns out this is an, yes, I'll change the slides as well. That's a good reminder. Like, yeah, my apologies. I just like got carried over. Okay. Yes. Okay. So basically, let's define here the boundaries and the boundary operator. So like formally speaking, if we have a simplex, right, boundaries, if we have a simplex of say dimension n, boundaries are the faces of this simplex. Formally speaking, they are simplices of dimension n minus 1, where one of the vertices is missing. All right, so for instance, if you take the simplex v0, v1, right, there is 2 boundaries, right? Because if you take the simplex v0, v1, you can either remove the vertex v0 and you get v1, or you can remove the vertex v1 and get v0. Okay. But by definition, boundary operator is given by definition. So by definition, boundary operator maps the simplex to the alternate sum of these boundary elements. And the alternation is done basically by multiplying each component with -1 to the power k, where k varies, like along the elements of the boundary. Right. So by choosing an orientation, right, we can formally write the boundary map as you see in the image. Right, you see the boundary map written for, like a one-dimensional simplex, the boundary map written for a two-dimensional simplex, and the boundary map written for 3D simplex, right, for a tetrahedron. Now, well, what would be the boundary map for the zero-dimensional simplex? Well, that would be simply the zero map, right? And this is expression of like, like another result, which informally is formulated as boundaries have no boundaries, right? Meaning the boundary map maps boundaries to the zero vector space. Right? Now, by definition, we're going to call a K-cycle a K-chain whose boundary is zero. Again, like a boundary is zero if the image of this boundary by the boundary map is actually zero, right? The zero vector space, right? Because images obviously are subspaces of the vector spaces, right? Now, like chains, cycles, and boundaries. Okay, so like recall, a chain was simply a linear combination of simplices in a certain dimension. Right? So like if we write the dimension in the decreasing order, right? So say, for instance, if we working with basically, like surfaces, right? We would start from dimension 2, move to dimension 1, and descend to dimension 0, right? We just would have like 3 elements in the chain. So like, so basically, again, like we form chains by taking linear combinations of these, like formal vectors and coefficients. Like where do coefficients come from? They can come from any field. The field of choice is the field, like Z2, and there is a good reason behind that, right? -1 in Z2 really equals 1, right? So, like the orientation doesn't matter, right? Number one, and also computations are very easy, right? Because you can basically use just like a binary number, right, to represent, a linear combination, right? Where 1 and 0 certainly are coefficients of the simplices, right? So it's computationally efficient, but it also like saves lots of pain, which is, associated with orientation. Now, the boundary map described before, right, maps cycles to boundaries, right? Cycles are indicated in the image by the zk plus 1, right? Sorry, like chains to boundaries and cycles to 0, right? So cycles, they have 0 boundary, right? So it was like defined in the previous slide, right? Well, that image just like illustrates this fact. Now, since we're taking quotient spaces, right? By definition, homology of the chain is really the list of the quotient spaces. Right? Now, like each of these spaces does have a dimension. Each of these quotient spaces does have a dimension, and this dimension is the Bethe number of that element of the homological chain. It turns out Bethe numbers are invariant. So, for instance, no matter how you triangulate a circle, right, you're going to get the list of Bethe numbers in each dimension as follows. In 0 dimension, you're going to get a 0, right? In dimension 1, you're going to get 1, and in dimensions 2 and higher, you're going to get a 0 because there is nothing in there really. Right? So basically, this sequence of Bethe numbers 0, 1, comma 0, 0, 0, like you can go infinitely so, like in any dimension, is an invariant of the circle, right? It's the homological invariant of the circle. So like it turns out, if you, like I'm jumping the gun, but I'm going to get there like eventually, right? If you have a data set and somehow like you show that the Petty number sequence for this data set is 0, 1, 0, 0, 0, right? There is a good reason to believe that this data set really comes from a circle or is sampled from a circle, right? However, this is not easy to do. So like the tool that allows us to basically draw such conclusions is called persistent homology. And so now that we know like what homology is, let's try to explain what is persistent homology, right? So at this point, I'm actually going to share my other browser and explain with an interactive tool how this is actually done. So let me go to Zoom and just like change what am I basically sharing. So that would be Safari, yes. Okay, here we go. Points from a circle, right? So sample a number of points, right? And let's say that we introduce some noise, like I'm just like moving these slides at random. So we did sample that kind of like cloud of points, right? So the theoretical manifold like is the circle. But as with, like every measurement that we do, there is some noise introduced, there is some error in the measurement, right? These points don't really like fall precisely on the circle. Now, how can we, like make an argument, like a scientific argument, that is to say these points have been sampled from a circle? Okay, so this is how. We know that each point is a simplex in dimension 0, right? Now, if we start encircling every point in a small ball, right, we're going to get basically like increasing balls, right, around each point. So you see now, like each point has a slight, a small kind of like greenish little ball surrounding this point. You see that where the two balls touch or intersect, there is a line segment joining these 2 points. So basically what we do, like we grow these teeny tiny balls around the points, and as they touch one another, we form simplices of dimension 1. If 3 balls would intersect, we form simplices of dimension 2, and so on. Right, so as we keep increasing this radius, we see more and more simplices forming, right, in dimension 1, dimension 2, dimension 3, and maybe dimension 4, and so on. As we increase the radius, we do see there is one noticeable thing. The hole in the middle is persisting, right? Is kind of like surviving, okay? Now, if we increase the radius to infinity, right? I don't know if we keep increasing the radius to infinity, the radius that surrounds all the balls, eventually the hole is going to disappear. But we see that this feature, sorry, my machine is just being slow, right? But imagine that the radius like is increased to infinity, and this hole will eventually disappear, right? So what is persistent homology like in simple terms? So that's not a mathematical definition, right? It's just like a description. Basically, it is how long does a topological feature persist as we keep connecting and these simplices with one another, right? So like here we see that this feature in dimension 1, this hole, right, in the middle, right, of the structure survives for a very long time, right? And this tells you that this feature is probably, an intrinsic feature of the original manifold where this data set was really taken from or measured from. That's what topological data analysis deals with, right? So like from this interactive tool, I'm like gonna go back to the slides. Just 1 second, where's my PDF? Yes. Okay. So now, like, yeah. Now, so what is filtration of a simplicial complex? Well, we call a simplicial complex a chain of simplices where every element of a previous element in this inclusion is a phase of the subsequent element. Right. So for instance, look at the first image labeled as 1. There is only one vertex, simplex of dimension 0. In the next step, we see another data point appears, right? That's another simplex of dimension 0. Now, the complex one, the simplicial complex one, which has just like point, is very humble, right? Very simple, is a subset of the second simplicial complex, just by virtue of inclusion. Now, if we look at 3, both point 0 and point 1, they are faces of this line segment. Faces of dimension 0, right? Just like vertices of this segment. Right? Then another data point appears, right? Then another edge appears, and then another edge appears. Right? So now this way we have a simplicial complex. You can basically assume that all these data points, they appear on time, for example, through a time series. Right? So basically we're measuring something, right? And at the initial time point, there is one value entering, into the data set. In the second, time slice, there is a second data element, and so on, right? Now, if you look at the straight lines below, H0 indicates the homology in dimension 0. And what do these long bars indicate? Well, look at the vertex 0. Vertex 0 appears at the time moment 1, and it kind of never disappears. It survives until the last complex. So basically, the very long line at the bottom of the graph indicates the lifespan of the vertex 0. Now, the vertex 1 shows up at the time moment 2, at the picture 2, if you like. And this is the next horizontal line sitting, like a little bit above the very long line. Now, the vertex 1, right, attaches the vertex 0 by the line segment 0, 1. So it kind of sacrifices himself in order to give us a simplex of the higher order, of the higher dimension, sorry. We say that vertex 1 dies. So the lifespan of vertex 1 is from the moment when it appears, which is the picture 2, till the moment when it disappears by becoming member of the vertex, of the edge 0, 1. So that's the lifespan of the vertex 1. It indicates a short living feature in dimension 0. Now, since vertex 1 is joined to the vertex 0, topologically speaking, right, these two vertices really, they contract into a point, right, through the line segment 1. So like this point is kept to be point 0. So basically, like topologically speaking, we collapse the line segment into the point 0, if we like to do so, right? Yeah, okay, so like vertex 0 persists because end of the day, everything collapses into a point, right? So the whole complex collapses to a point, right? If we collapse manifold to a point, right, you take the whole real line, you can, topologically speaking, you can collapse the real line to a point. And in order to do that, you have to choose a special point. And for this purpose, you, for example, can choose the origin of the coordinates, right? So in this picture, I have chosen 0, the point 0. That's the reason, yeah. But great question, it's totally valid. Same can be said for the vertex 2, like it is born at the picture number 4, and it dies at the picture number 5. And we see at picture number 6, finally, we see a feature in dimension 1 that does appear, and it never disappears. Right. This is indicated by the small arrow labeled by H1. Right. So now, the collection of all these lifelines, so you see, like all these segments, they are lifelines of various topological components of our data set. Right? That set of lifelines is known as the barcode of our data set. So like, although, you know, like every feature, basically, if you recall the tool that I did share with you like previously in my browser, right? This tool tells you that eventually the whole data set, if we increase the radius of these balls to infinity, it's gonna like collapse to a point, which is pretty boring. But on the way from like the original cloud of points, right, to this individual point where everything collapses in a single point, we have many interesting features appearing and disappearing. That feature set is captured by this barcode. Yeah. So now, like this barcode can further be formalized into a module, but you know, the scope of this talk doesn't really let us get there. But you know, like afterwards, basically, afterwards, I can't really like chat after 5 because I have an exam. I have to invigilate an exam. But like at another time, you know, like contact me individually. You know how to find me, and I can very happily describe that process. But it is harder, and it's kind of like gonna get very boring if I do that. Right. So that was the link to the tool that I use for demo. Now let's summarize what we did so far. So we started from a data set, from a cloud of points, right? We did build a geometric filtered complex on top of this data set. How did we do this? Well, we kind of like grew balls around the points, and we connected points if the balls will eventually intersect, right? If 3 balls intersect, we make a triangle. If 4 balls intersect, we make a tetrahedron, right? If 5 balls intersect, we make like 4D tetrahedron, right? And so on. Now, additionally, we compute these barcodes. Now, these barcodes indicate the birth time and the death time of a component, of a topological component. So they are just like a pair of numbers. So each barcode can also be represented as a pair of numbers, but pairs of numbers can be plotted on the plane, right? So the points, the barcodes plotted as points on the plane, make up the so-called persistence diagram of a topological complex. And there is Python tools that can do that, right? There is tons of tools out there. Like, yeah, that I can happily share, you know, like afterwards, you know, like tools if you like, or like once I'm kind of like done with this, I can actually like show you some of these tools. All right, so now that we do understand that we have a way, you know, to start with a cloud of points and say something about the manifold where these points come from. And this can be very important, right? Because these manifolds, they tell us about something about the real world object, right? So like as we like head towards the applications, right? Let's actually see how can we let's work our way like to some applications, right? So this way goes through the so-called Morse theory. So Morse theory originates many years before topological data analysis, right? Topological data analysis is born basically in 2000. It's a very new mathematical discipline, right? Morse theory dates back, you know, like it has been created by Marston Morse, and the example that I'm citing comes, you know, like from a very old, you know, like Morse paper. Right? So what does Morse theory talks about? So like Morse theory talks about functions, smooth functions over smooth manifolds. If you look at the image painted in pink, right? That's a smooth surface, right? In you know, like a two-dimensional smooth surface embedded in the 3D space, and it has two holes, like and three handles, as you can see. And certainly there is a void inside it. Now, homologically speaking, so like if we compute the homology, you know, like of this space of this surface, right? This surface has one connected component, right? So number of connected components is the dimension of basically the Betti number, right, in the zero dimension, right? The Betti number in one dimension is number of you know, like circles, right, or basically one-dimensional features, right, or linearly independent one-dimensional features, right? So now, if you look at the circles that wrap around, right, you can find out, like that's basically an exercise, you can find out like 4 linearly independent circles that wrap around, right? Well, you could argue that there are 5, but in fact, the 5th one is a linear combination of the other 4, right? So that can be shown. Right? And in dimension 2, basically, there is just like a void inside. That's a single void, right? You know, like if there is a small end inside this kind of like surface in the inner, you know, in the inner body of the surface, it can go anywhere, right? That should be intuitively clear. So these are basically the Betti numbers, right? Or the homological invariants, you know, of, or rather the, you know, the list of, you know, like homological dimensions of in each dimension, right? So where is the link with topological data analysis? Let's take, on this manifold, let's define a Morse function. What is a Morse function? You can think of a Morse function as a smooth function, that it is generic in the sense that it doesn't have duplicated critical points. So basically, each critical point is unique. Such a function of this surface is, for example, the height from the plane where this surface is supported, right? You see the pink plane below, right? And you compute the height. For each point on the manifold, you can tell what is the height, right? And it is not very hard to see that the critical points of the height function, they are basically indicated by these pink dots, right? It's basically where, you know, like the kind of like the tangent plane to the surface is parallel to the horizontal, right? But this is where critical points are. Right? So now, another component that we're going to need is the so-called index. So like, what is index of a critical point? The index of a critical point is the number of orthogonal dimensions in which the function decreases. So for example, if you look at one of the top points of this surface, right, either left or the right, if you make a plane tangent to that point at the top, there is 2 orthogonal directions in which the height function decreases, right? Basically, if you are at the top of the hill, no matter which way you walk, you're going to walk down. You cannot walk up, so the height is going to decrease, right? And since the tangent plane to this point has 2 dimensions, right? The tangent space to this point has 2 dimensions, right? The index of this critical point is 2, right? If you look at one of the points that are at the lower end, right, supported on the plane, right? One is supported on the plane, one is a little bit higher, but at each of these, really the index is 0 because the tangent, you know, like if you look at the tangent plane there, no matter how you walk on the surface, the height is going to increase. There is no decrease, right? The saddle points are the points which are basically around the holes in the structure. There, in one direction, the height increases, in the other direction, the height decreases, right? Around these saddle points. So these indices, they are 1, right? So at the top values, the indices are 2, at the bottom, you know, points, the indices are 0, and at the saddle point, they are 1, it turns out, right, that one can link basically the number of critical values of index k with the Bethe numbers with the formula that it is below the photograph of the Marston Morse. So what is MT? Well, MT is a polynomial that it is obtained by summing up for each k the number of critical values of index k times some formal variable to the power k. And so basically, if we like to write down this MT right now, right, we would have to count in dimension 0, right? Sorry, no, not in dimension 0, but like how many critical points have index 0? There are 2 of them, right? The bottom points. So we would have 2 times t to the power 0 plus. Now, like, what are the points with index 1? Well, there is a saddle points. How many saddle points? There is 4 saddle points, right? So we would have plus 4t, right? And then we would have, you know, the 2 top points with dimension 2 plus 2 times t to the power 2, right? So that would be the polynomial MT. The polynomial BT is something similar, but the coefficients are Bethe numbers, right? BT on the other side is basically the number of pairs birth death of if you compute the persistence diagram. Right. So there is a link between these polynomials, and that link is indicated by this equation, like below Morse's photograph. Right. So where are the applications of this? Okay, so like, oops, sorry. Okay, so sounds great, but I just want an application. All right. So let's look at the image of this hand. That's a 3D, you know, that's a 3D, obviously, object, right? And we would like to figure out, you know, like special features, right? Now, when we sample points by reading off the coordinates, right? And if you turn this hand sideways, you might not be able to see 5 fingers at all, right? You might see one solid thing, right? Or you might rotate it horizontally, you might not be able to see, you know, like that well, what you need to actually see, right? So we need to do better, right? We need basically to consider something intrinsic to this object in order to compute its features, right? Because obviously these features are intrinsic. So like if you imagine an ant, so look at the black point in the middle of the red colored part. That black point, imagine that that black point is an ant, right? And suppose that the origin of the ant's coordinative system on the hand is the initial point in the first image, right? Now that ant has a very special property, right? It can walk along geodesical lines, which are basically lines with the shortest distance from the initial position of the ant, right? That's what we're going to call geodesic distance for the ant, right? So as the ant keeps covering more and more territory, right? Initially, we don't distinguish anything interesting, right? So we move from image 1 to image 2, there is nothing much interesting. The whole ant territory can collapse to a point, which is not very interesting. As we move to the next image, right? Still, there is not many interesting things, right? So the ant is just like, kind of like, the ant's territory is kind of like spilling behind the hand, right? And now we just distinguish one hole, right? It's basically, if we think that of that red cloth kind of wrapped around the hand, there is basically only one hole at the top, right? The bottom is still kind of like featureless, so to speak, right? So as we progress in the image 3, things get much more interesting, right? So now there is 5 holes, right? As we keep kind of like increasing the ants' territory, right? These holes persist, right? Until obviously they disappear, right? So at the rightmost image, everything disappeared, right? So now we have one connected component. The persistence diagram has 5 distinguishable points. It is shown on the right-hand side of this image. So that tells you that basically this object that we got has 5 distinguished features. It's the 5 fingers, right, that this ant have. So is there more applications out there? Like, sure, there is even more, but you know, like I'm just going to talk about one of these applications, right? For instance, a very interesting application is in neuroscience, right? So if you consider brain regions, what is a brain region? Well, a brain region is a small cluster of neurons concentrated about one geometrical point in the brain, right? We know that each brain region at all times exhibits electrical activity, but sometimes this electrical activity is local. Sometimes it's electrical activity that extends to remote regions, right? So we would like to know, right, how many of these regions are connected, right? And what is their role into various, you know, like brain conditions or brain disease conditions, right? For example, Alzheimer's or other, you know, like medical conditions, right? Now, since here we are talking about connectivity, right? Well, that means we're just looking for connected components, right? Connected components, but recall, number of connected components is simply the Bethe number in dimension 0. Right, so right now, right, we are kind of like talking topology, right? So basically, we read off that connectivity of brain regions, for example, from an MRI, and we are able to say that, well, the Bethe number in dimension 0, like for a very long time, remains, for example, 5. So there is 5 regions on the brain that constantly communicate for a very long time under whatever conditions, communicate with one another for this patient. For another patient, might be 15, maybe 20. So once you generate some statistics, like on this, certainly you can use, you know, like other machine learning tools in order to build a classifier that can tell between like a healthy brain and a brain suffering from a specific condition. So yeah, like, thank you very much. Questions?
That was so cool. Yeah. I really like the applications thing. I didn't expect it to like go into neuroscience and stuff.
Well, I mean, this is where my personal research is actually in neuroscience. You know, I basically try to like apply topological data analysis into the data of epileptic patients.
Makes sense. Someone in the chat is asking if there are any resources we can check out to learn more about this.
Sure. Okay. So basically, a good starting point is a book. The author's name is Eldez Brunner, right? And it is called Computational Topology. The book is published, I think, in 2007. I mean, just like DM me, like in some way, like on Discord or something, and I'd be very happy to share resources. So this is a starting point, right? If you like to start with topological data analysis. Another very interesting thing to do is look at Python packages that actually do computations, right? So like one of these packages that I do use like on a constant basis is called RIPS, RIPS, just like Google it, it's RIPS. It's used to compute the so-called Rips-Viatoris complex, which I did describe in the slides like a little bit before. And it also gives you persistence diagrams. right? So basically, if you have like some sort of like experimental data set and you like to look at some application, that would be very useful. Another element that you guys might find very interesting is actually the sensor network coverage. So like imagine you have, you know, these routers, right? These internet routers, I don't know, a DH building or something, and you'd like to know, you know, if there is areas that are not covered, right? So, or what areas are not covered? Where do you need a new route? So basically what you do, you go measure the strength of the signal in different points, right? Construct, you know, like the persistence diagram of your data points, and you see for holes in dimension 1. So you see for persisting features in dimension 1. Right? These persisting features, they tell you that there are kind of like circle-like areas or closed areas where Wi-Fi is not good. It's at the center of the circle, you should add a new router. So here you have a scientific argument, you know, like to convince the management of, you know, like UDM that, well, in this area, the coverage is not good, we need a new router, right? So for instance, that's, and yeah, like, so basically for resources, just like, I figured now I should have included some resources in the slides, but I simply forgot. So just contact me separately.
All right, thank you so much for the talk. And it's almost 5 p.m. So I think we can let Ilir go so he can go torture Scarborough students.
Yeah. Thank you.
Thank you for the great talk. We'll be sure to
Thank you for the
follow up.
invitation. It was fun. Thank you very much.
Yes. All right. See you.
Yeah,
Goodbye, everyone. Have a nice day.